Hey everyone, this is going to be a 13.2 overview. We are in a chapter that's kind of focusing on physical states. All right, sorry, that was a little interruption with an announcement. So this chapter is all about physical states. The next chapter is all about gases, so we're definitely going to be focusing there, and we're going to combine these two chapters for our next assessment. But 13.1 covered your gases. 13.2 was looking at liquids, but more specifically, this change from liquid to gas, which we're going to talk about in a second. And then 13.3 is going to be heavily focused on solid. Section 13.4 will have information on all three of the states and their interactions with each other. But for now, we're going to focus on 13.2, which is looking at this change from liquid to gas and the various ways that that happens. So in this transition, we can call this vaporization. We can call this evaporation. And we can call this boiling. All three of these words are acceptable for the state change of liquid to gas. Now, if we look at these three words, this one, vaporization, is becoming a vapor from a liquid, and it includes both evaporation and boiling. So these two bottom ones are a type, each of those are a type of vaporization, okay? Now we're gonna look at evaporation in a little bit more detail, okay? First of all, I want to do a little visual. So I've drawn a little beaker of liquid here. And if you can imagine, if I could push play on this little drawing, all of these water molecules or liquid molecules, waters are most common, but anyway, our liquid molecules would be rolling around each other within the beaker, okay? They would be touching each other. I know I drew them spaced out a little bit here, but they're gonna be touching each other, rolling around each other, constantly moving, transitioning through the beaker from one place to another, bouncing off of each other, reversing directions, things like that, but always in contact with all the other molecules around them. Okay, now evaporation happens only at the surface of the liquid. And what happens is these molecules are all attracted to each other somewhat. That's why they're a liquid. But if one of these molecules at the surface gets moving fast enough, it might have enough energy to leave the liquid, because that energy, that speed is enough to escape the attractions to its neighbors. And that happens over and over and over. We might have another one over here that escapes this way. At the same time, one of them that already escaped, you know, let's say that there's a molecule that escaped over here. It might bounce back, you know, or it might bounce off of a gas molecule. Like say there's a gas molecule right here. If I have a water molecule here, it could bounce into that gas molecule and right back into the liquid, okay? So, but these are all going to start escaping this open container over time, and that is going to cause the water level to decrease, the liquid level to decrease. So that's evaporation. It's happening at the surface. Now remember, the molecules that are able to escape are the ones that have high energy. They have enough energy and they're at the surface, so they can overcome those attractions that are holding them in the beaker. So the high energy particles escape the beaker, and what's left behind are all of the particles that have lower energy on average. We're losing the highest energy particles. That means that the ones behind have a decrease in energy. Decreasing energy, I'm gonna put average up here, okay? Decreasing average energy because we're losing these high energy pieces from the top. Remember from section 13.1 that average kinetic energy is how we measure temperature. So average energy is how we measure temperature. So as these high energy particles leave, the average energy is decreasing, and that means that evaporation is a cooling process. And there was a blank for that in your notes packet. What happens to the temperature of the liquid left behind as evaporation occurs? Again, the temperature is going to go down because the average energy of the particles that are still here is going to be lower. We just lost some high energy pieces. So now the average energy of what's left is lower, which means a cooler temperature. Evaporation is a cooling process And that's what you should have written in that blank. All right, let's talk about how temperature affects evaporation. Well, if I heat this beaker, let me draw a little, well, let me just do a Bunsen burner flame here. Because we know that Bunsen burner flames look something like that, okay? So Bunsen burner flame under a giant beaker of water, I'm gonna start heating that beaker up. Well, remember, we have to know what temperature means. Temperature is the average energy of the particles. So if we are heating this beaker, these particles are going to move faster. They are going to have more energy. And if all of the particles are moving faster, the number of particles at the surface that have enough energy to escape the beaker, to evaporate, is going to increase. So when you heat a beaker of liquid, it is going to evaporate more quickly because the number of particles that have enough energy to escape is going to go up. All of these particles are gaining energy. The ones at the surface that have enough to escape, that number is going to increase. Okay, so that makes evaporation happen faster. All right, I think that's all we have to cover for evaporation. Real quickly, we've talked about pressure. Air pressure is caused by collisions. So if I have an air molecule and it collides off of this beaker like that, okay, it's flying over to the beaker, it collides off, that creates a pressure, that collision. When we measure air pressure, we're measuring the number of collisions, the force of those collisions with a surface. When you're looking at a pressure inside a beaker right up here above this liquid, you not only have the air pressure from these air particles, but you also have some added pressure from these liquid particles that are escaping. That is called vapor pressure. So vapor pressure is just measuring pressure right above a liquid. And it tends to be slightly higher than the pressure in the same room, but on the outside of the liquid, because you have additional particles escaping the liquid and adding some collisions there, making a little bit more pressure. Okay, so vapor pressure, pressure measured above a liquid. Okay. All right. Again, temperature, when you increase it, there's more evaporation. That means more liquid particles escaping, so that's higher vapor pressure. And liquids that evaporate more easily are going to also have higher vapor pressure because they're sending more molecules into the air. All right, switching gears, boiling point. Let's talk about boiling. Okay, so the definition of boiling in the book is correct, but it's a little overcomplicated. It's the temperature at which the vapor pressure is just equal to the external pressure on the liquid. All right, so let's go back at the drawing here. There is a pressure on the liquid from air particles coming down like this, okay? And that pressure keeps most of the molecules in the beaker, and just very slowly over time, well, depending on the liquid, could be fast, but over time, particles will escape that don't get bounced back off of one of these air particles. And then you just decrease your liquid, right? Now, boiling happens when all these particles have increased in energy so much that all of these particles at the surface have enough pressure, enough energy to overcome that surface pressure. So the pressure here and the pressure here are equal. That means that these are all going to start turning into a gas throughout the liquid, okay? We're going to end up with bubbles of gas where these molecules have all turned into gas inside the liquid at every place. This is a really bad drawing. I'm gonna just fix that, okay? But we're going to see gas formation everywhere in this beaker when it's boiling. It is not just happening at the surface. Surface transition is evaporation. Throughout the beaker, throughout the container, throughout the liquid, that is going to be boiling. So when you see bubbles at the bottom of your pan, when you're boiling, when you're trying to boil water, that's almost there. You see these little tiny bubbles form, and then as soon as they raise up off the bottom of the pan, they turn right back into a liquid. They recondense, okay? When that starts happening throughout the liquid, you're gonna get bubbles forming at the bottom, bubbles forming on the sides, bubbles forming in the middle of the pot, bubbles forming at the surface. That rolling boil, that is boiling. That is the temperature at which you have that equal pressure coming from the top and equal vapor pressure coming from the bottom, okay? Now, I don't need you to know that pressure definition of boiling. What I want you guys to know is that boiling is happening all the way throughout. So in the notes packet, we've got boiling point, and I want you to write a class definition for that as well. Just again, a little bit simpler definition and focusing a little bit differently. Okay, so this is the temperature. The temperature at which a liquid turns into a gas And at the beginning of the year, that probably would have been our entire definition. Okay, but we're going to add a little bit more to it now that we're kind of trying to differentiate between evaporation and boiling. Okay, so at which a liquid turns into a gas throughout the liquid, not just at the surface. Throughout the liquid, not just at the surface. Not just at the surface. Okay, so the parentheses piece isn't super important here, but the temperature at which a liquid turns into a gas throughout the liquid, that piece is kind of the new piece today. Okay, we need you to understand evaporation happens at the surface of a liquid, boiling happens throughout the liquid. So if the change, the liquid to gas change here is not happening everywhere in your sample, then it's not boiling. It could be on the verge of boiling if you're seeing bubbles down at the bottom of your container where your heat source is, but it's not boiling until it's happening throughout the liquid. Okay, what else about boiling? We had a couple things in here. Altitude's effect on boiling. Now, if we go back to that pressure description, remember, it's when this downward pressure from the air and this upward pressure from these molecules that are escaping are equal. Okay, so altitude, when you go up in altitude, when you increase altitude, you decrease pressure, which means that the force coming down on this liquid will get smaller. And if you make that force smaller, then you don't need as much force going in the upward direction here in order to get boiling, which means you don't need as much energy, which means you don't need as high of a temperature. Okay, so when you go up in altitude, you have lower air pressure, which means you're going to have lower boiling point. You're gonna have lower boiling point. Okay, less pressure on the liquid means it's easier for the liquid to escape, so it's a lower boiling point. All right, other things that affect heating or we did altitude. Okay, heating. Let's talk about heating a boiling liquid. Okay, if this was already boiling, it's changing from liquid to gas throughout this container, and I continue to heat it with my little tiny Bunsen burner flame or any stove or whatever, the temperature of this liquid will never go above its boiling point. So if we're at sea level and we heat water to 100 degrees Celsius, it will be boiling. Okay, and if we continue to pump the heat in there, it doesn't matter how much. Okay, we just push and push and push more heat, it will stay at 100 degrees Celsius while it's boiling. It cannot go above its boiling point because it will no longer be a liquid when it does. So at 100 degrees Celsius, you end up with a pause in the temperature increase. It will not increase above that. Once all of the water is gone, your container can start getting a lot hotter. Your container probably already is hotter if it's made out of metal, for example. But the H2O vapor, the gas that you create, that can raise above 100 degrees Celsius. But the water, the liquid water itself, can never go above 100 degrees Celsius. It will boil faster, but it will not increase its temperature. Okay, it's a weird concept, but it will not increase its temperature. You'll have liquid water here and you're heating it. This is a graph here. Okay, let's say temperature versus time. Okay, you heat some liquid water, it will heat. Once you hit this 100 degrees Celsius mark, it will just plateau and it will be boiling, boiling, boiling. And then once all of the water is not liquid anymore, it is all in gas form, then the temperature will start to increase again. So in this window right here, and it just depends on how fast you heat it, this is boiling water. That's our boiling water window where we plateau at that temperature, and it's going to be a mixture of water liquid and water gas. You've got those water air bubbles, water gas bubbles, excuse me, and you have the liquid water around them, and it's a mixture. Once it's all gas, the temperature will start increasing again. So it's a really fascinating concept. It also works down here at freezing. So at 0, you end up with this, the water starts to freeze, and it will not cool below 0 until you get it all solid, and then you can cool that ice down even further. So anyway, that's a concept you'll get more of if you take an advanced chemistry class like AP or college chemistry. All right, moving on beyond that, the last thing I want to talk about is normal boiling point. Normal boiling point is at sea level, okay? In the book, it said it is the boiling point of a liquid at a pressure of 101.3 kilopascals. That is absolutely correct, but where is the pressure, 101.3 kilopascals? That is the defined pressure of sea level. So when you put the word normal in front of boiling point, melting point, whatever, that word means at sea level. Okay, at the pressure, the standard pressure of sea level. So really, it technically means at standard pressure, which is the pressure at sea level. Okay, all right, that's our 13.2 overview. Hopefully that was helpful. Make sure that you get those class notes written and keep working on those assignments, and we will see you in class. Make sure you reach out to us if you have any questions.